Hello everyone. In this video we are going to discuss about some problems on laser and we'll discuss about their solution. So let us go to the first problem. The first problem is, let me read it out. A laser beam has a power of 100 milliwatt. It has an aperture of 5 into 10 to the power minus 3 meter and a wavelength of 7000 angstrom. The beam is focused with a lens of focal length 0.1 meter. Calculate the aerial speed and the intensity of the image. So what are the given parameters here? The given parameters are, first the wavelength is given, it is 7000 angstrom. We have converted into 7000 into the power minus 10 meter. The diameter of the aperture we have considered D, we have named it as D, 5 into 10 to the power minus 3 meter. Focal length is given as 0.1 meter and power of the laser beam is 100 milliwatt, which is 10 to the power minus 1 watt. Now the angular spread, as we know from our previous knowledge of optics, is that d theta equal to 1.22 into lambda by d, where lambda is the wavelength and d is the diameter of the aperture. We put all the values because lambda is known to us and the diameter of the aperture is also known to us. So we get the angular spread. Now as soon as we get the angular spread, we'll find out the aerial spread, which is actually needed to be find out the requirement of this problem. So the first one is the aerial spread. So aerial spread, how do we get aerial spread? It is d theta into f, that is the focal length, square. So we have put all the values because previously we have found out the angular spread. So it is angular spread into the focal length. So here is the answer. It is 2.92 into 10 to the power minus 10 meter square. And the second part of the question, if we divide into A and B, so A is the aerial spread that we have already found out, and intensity. So as we know, intensity is equal to power by area. So the area here means the aerial spread. So power is given as 10 to the power minus 1 watt, and area we have already found out as 2.92 into 10 to the power minus 10 meter. So we put all the values, so we get the intensity here. So this is problem number 1. So let us move on to the next problem. The second problem which is given here is, let me read it out. Laser emission occurs from 3s to 2p level transition in helium neon laser, and a laser of 6328 angstrom wavelength is produced. We are required here that calculate the pumping energy required if 2p level has energy equal to 15.2 into 10 to the power minus 19 joule. Assume no loss in the process. So first of all, we need to know about the helium neon laser transition. So here you see I have drawn the transitions in the energy diagram of the helium neon laser. So you can see here for the neon laser, we have, for the neon atom, we have 1s level, we have 2p level, 2s level, 3p level and the 3s level. Now the aim of the question, the goal of the question is to find out the pumping energy required. Pumping energy required means we have to find out how much energy is required for a atom to move from the ground state to the 3s state. Why 3s state? Because from the 3s state to 3p state, the transition is taking place and a laser of wavelength 6328 angstrom is being produced. So the total energy will be from this neon grounds, from this ground state to 3s energy state. So this total energy we have to find it out. Now you see here, from this ground state to 2p level, the energy is already given here in the question. In the question it is already given. So it is 15.2 into 10 to the power minus 19 joule. So the total pumping energy will be the energy from the ground state to 2p level and from 2p to 3s level. So that is the energy of the 2p level as well as the energy of the photon. because we know the wavelength of the photon. So if we know the wavelength of the photon, it will be easier for us to find out the frequency of the photon. So if we find the frequency of the photon, we know h nu is the energy, and if we find out that energy plus the energy of the 2p level, we'll find out the pumping energy. That is what I have done in here in the solution. So it is the energy of the 2p level. Total pumping energy will be energy of the 2p level plus the energy of the photon. So the energy of the 2p level as given in the problem, 15.2 into 10 to the power minus 19 joule, and h nu is c by lambda. So we put the value of the Planck constant, we put the value of the velocity of the light, and lambda is given here as 6328 angstrom, and we convert it into meter. So finally we get the energy as 11.46 eV. That is the total energy. We have converted into from joule to eV, because 1 eV is 1.6 into 10 to the power minus 19 joule. The third problem is the wavelength corresponding to an energy gap is given as 6500 angstrom. Find the ratio of the population of the two states in thermal equilibrium at room temperature. The room temperature is given as 27 degree centigrade. Now we have considered here the two energy levels E1 and E2, where E1 is the lower energy state and E2 is the upper energy state or the higher energy state. N1 is the population in the lower energy state and N2 is the population in the higher energy state. Now, as you know from the Boltzmann distribution law, in thermal equilibrium, the population ratio is governed by this law, which is given as N2 by N1. It is equal to e to the power minus E2 minus E1 by K into T, where E2 minus E1 is the energy difference between the upper level and the lower energy level, K is the Boltzmann constant, and T is the temperature. So here we have to find out this ratio, that is N2 by N1. So what is given in the problem is the lambda is given. So lambda is given as 6500 angstrom. So E2 minus E1 is h nu, and we know that nu equal to c by lambda. So E2 minus E1 equal to h nu is hc by lambda. So N2 by N1, the ratio is equal to e to the power minus h nu by kt, or we can write it as e to the power minus hc by lambda kt. So what we know, we have the Boltzmann constant, we know the temperature, and we know the Planck constant. So we have put all the values, and we know the velocity of light, and lambda is also given. So everything is given. So we put all the values and we get the population as 8.375 into 10 to the power minus 33. So this is problem number 3. Let us move on to the next problem. Our next problem is, at what temperature are the rates of spontaneous and stimulated emission are equal? For this, we need to know about the Einstein coefficients. Let us consider R as the ratio of these two emission, that is rate of the spontaneous emission by rate of the stimulated emission. Rate of the spontaneous emission is equal to A21 into N2, where N2 is the population of the upper energy state, as I have drawn the picture in the previous problem, and A21 is the Einstein coefficient for spontaneous emission. And for stimulated emission, this is B21 into N2 into U nu. What is U nu? U nu is the energy density. So from the derivation of the Einstein AB coefficient, we know that we can write this from the Planck constant law, U nu as 8 pi h nu cube by c cube 1 by e to the power h nu by kt minus 1. And from Einstein AB coefficient, A21 by B21 is also 8 pi h into nu cube by c cube. So if I put that value here, this 8 pi h nu cube by c cube, it gets cancelled, and what we are left with, the ratio of the rate of spontaneous emission by stimulated emission is R is equal to e to the power h nu by kt minus 1. So this complicated thing gets simplified. So if now in the question what is given, now these two rates are equal, that means R is equal to 1. So that is e to the power h nu by kt minus 1 is equal to 1. So e to the power h nu by kt is equal to 2. So we need to find out the temperature at which these rates are equal. That means lambda is given here as 7000 angstrom. Frequency nu is c by lambda, which we can easily get because lambda is given here. So h nu by kt, it becomes h is known, nu is known, and we know the Boltzmann constant, only t is unknown. So from here we can easily find out h nu by k, we put all the values here, so we get it as 20 into 20.53 into 10 to the power 3. So we put it back in this equation, e to the power h nu by kt is equal to 2, where we solve for t and we get t as 29,627 Kelvin. So this is about problem number 4. So let us move on to our last problem, problem number 5. Find the ratio of the spontaneous emission to stimulated emission for a cavity of temperature 50 Kelvin and wavelength 10 to the power minus 5 meter. So here what is asked here to find out is the ratio only. So in the previous problem, as we have already discussed, that the ratio of the, you have seen here let us go back to the previous problem, problem number 4, that rate of spontaneous emission by rate of stimulated emission is given as e to the power minus h nu by kt minus 1. So I have directly written it here, that R is equal to e to the power h nu by kt minus 1. So here the problem is already simplified because we need to find out the R here, the ratio of the spontaneous emission to simulated emission. So what is given here, it is the temperature is known here, that is 50 Kelvin. One thing we should always remember, that in the previous problem you see here the temperature is temperature we found it in the Kelvin. So if here in this problem also the temperature is given here in Kelvin, 50 Kelvin. So if the temperature is ever given in Celsius, so we have to convert it into Kelvin, then we'll apply it in the problem. So every temperature has to be converted into the Kelvin scale. So here, so coming back to the problem, we have all the parameters given here. We know nu here because lambda is given here, wavelength 10 to the power minus 5 meter. So we can easily convert into nu, and a Planck constant we know, Boltzmann constant we know, and temperature is given here. So putting all the values, we find out that the ratio is coming as e to the power 28.8, which is 3.218 into 10 to the power 12. So these are all about the laser problems. We'll come back with more problems and solution and more videos on laser and this applied optics. Thank you. If you like the video, subscribe, share and hit the like button. Thank you all.